Let's take a look at the subskills for chapter 6. The first example is comparing and contrasting solving linear equations versus quadratic equations. So first you'll notice in 1a, when you have x plus 5 equals 3x minus 7, the only variables are x. So there are two terms that have a variable, but both of those terms are x. In this case, x and 3x. Each of those only have an x. Whereas on 1b, we have one term with an x squared and another term, this negative 6x, has an x in it. So because the highest power in this equation is an x squared minus 6x minus 27 equals 0 is a quadratic equation. So let's go ahead and look at how we solve each of them. For 1a, we notice it is linear. Again, one thing you might notice is that there are no x squareds or y squareds or an xy or a square root of x. There's just different terms with constants and just an x in it. So we also may notice that we have the two terms that have x in it, but they're on different sides of the equation. So the first thing we could do is get all of our x's to one side through adding and subtracting. So in this case, I will choose to subtract x from both sides to get 5 equals 2x minus 7. And now we're ready to add 7 to both sides. We get 12 equals 2x. Divide both sides by 2 to get 6 equals x, or x equals 6. On 1b, we see we have x squared minus 6x minus 27 equals 0. And in this situation, we have an equation of the form ax squared plus bx plus c equals 0. So in this case, the coefficient in front of x squared, or a, equals 1. And so our factoring can be a little easier. Now, one property that we're going to use is that if we know that a times b equals 0, and this is specific to multiplication, if we know that a times b equals 0, then we can say that either a has to equal 0 or b equals 0. So we're going to go ahead and put these two strategies together. And again, if we have a equals 1, then we can just use that trick of finding two numbers who multiply to c and add to b and use that to factor. So in this situation, we can see what two numbers multiply to negative 27 and add to negative 6. And so we go through different things that multiply to negative 27. 1 and 27 might work, but those will not add or subtract to negative 6. So then we try some other factors like 3 and 9. And if one of them is negative, they will multiply to negative 27. So we need one positive, one negative. But because they add to negative 6, we need more negatives. So positive 3 and negative 9 multiply to negative 27 and add to negative 6. So that allows us to factor x squared minus 6x minus 27 into x plus 3 times x minus 9. And all of that will still equal 0. And now using this zero product property, we can say that either x plus 3 has to equal 0 or x minus 9 must equal 0, because those are the two quantities multiplying to equal 0. So we solve each of those. Subtracting 3 from both sides gives us x equals negative 3, and adding 9 to both sides gives us x equals 9. So our solutions are negative 3 and positive 9. Okay, So here, notice that when we are solving a linear equation, we're getting all of our variables to one side and all of our constants to the other side and isolating x. Whereas if we have a quadratic and if it is factorable, we're going to set it equal to 0, factor it, and then set each factor to 0 and solve. All right, let's look at some more quadratic equations or higher power equations with higher powers of x. Let's take a look at x squared minus x equals 20. So here we see, again, we have an x squared term and a term with just an x. So our strategy is going to be to set it equal to 0. And I'd like to keep that x squared positive. So I will subtract 20 from both sides. And I get x squared minus x minus 20 equals 0. Notice you cannot subtract the 20 from x squared or negative x because they are not like terms. Again, we have something of the form x squared plus bx plus c. So we can see what multiplies to c, or negative 20, and adds to negative 1, that coefficient in front of x. 1 and 20 multiply to 20, but will not add or subtract to 1. 2 and 10, same thing, but 4 and 5 might do the trick. One would need to be positive, the other negative. And since I need more negatives, because they add to negative 1, let's see, negative 5 and positive 4. So 4 times negative 5 equals negative 20, and 4 plus a negative 5 equals negative 1. So we can factor this into x plus 4 and x minus 5 equals 0. So now that it is in factored form equal to 0, we can set each factor to 0 and solve. With x plus 4 equals 0, we'll subtract 4 from both sides to get x equals negative 4. And x minus 5 equals 0. We'll add 5 to both sides to get x equals 5. That gives us our two solutions, negative 4 and 5. And notice our degree of this polynomial is degree 2, and we got two solutions. So let's take a look at B and see how many solutions we'll get here. So first things first, we now have a cubic, and we're hoping to possibly get it down to a quadratic because we have a lot more strategies with our quadratics. So I would like to keep our highest power of x positive. So since x cubed is positive, I'm going to move everything else from that right-hand side over to the left. So I will add x squared to both sides, and I will subtract 12x from both sides. And that will give us x cubed plus x squared minus 12x equals 0. So now that it's 0, we can utilize our factoring in order to solve. Now, we know we don't have just a quadratic because our highest power is the third power, or a cubic. So we may notice that all three of these terms contain an x. So one strategy for factoring in general is that first step you want to see, is there a GCF? Is there something that all of these three terms have in common? And in this case, they all have x in common, so we could factor out an x. So once I factor out one x from x cubed, I'm left with x squared. When I factor out an x from x squared, I'm just left with an x. And in that last term, we'll just be left with negative 12. Now, inside the parentheses, we have an x squared, an x, and a constant. So now we are able to apply what multiplies to negative 12 and adds to 1. So we go through our factors, we come up with 3 and 4. Since we need them to multiply to a negative, one positive, one negative, but adding to a positive, we need more positives. So positive 4, negative 3. So bring down that x, and then we get inside the parentheses, x minus 3 and x plus 4. Now we're ready to set all three of those factors to 0. So x equals 0, x minus 3 equals 0, or x plus 4 equals 0. X equals 0 is already solved for, but x equals 3, we can add 3 to both sides or just get x equals 3. X plus 4 equals 0, we'll subtract 4 from both sides to get x equals negative 4. So now our solutions are negative 4, 0, and 3. While it's not required to list your solutions from least to greatest, it's common to do so. Let's go take a look at a couple more cases of our quadratic equations. So here you might notice on example C, we have x squared minus 27 equals 0. So now we have an x squared term, but no x. So this is when we have an x squared term, but no x, or no x term alone, then we can use the square root method. And so what we're going to do in this case is we will isolate that x squared. So I will first add 27 to both sides. And now we get x squared equals 27. And I can utilize the square root method, which states that I can take the square root of both sides of the equation, but I do get a plus or minus. And so that gives me x equals plus or minus rad 27. And notice the square and the square root will cancel out. So I'm just left with x. And now we have to observe or see if we can simplify square root 27. So off to the side, I might say, oh, well, square root 27 can be written as rad 9, which is a perfect square, times 3, or 3 rad 3. So my final answer will be plus or minus 3 rad 3. Notice that there is the highest power of x is x squared, and we are expecting 2 answers. And in fact, there are, because we get positive 3 rad 3 as a solution and negative 3 rad 3 as our other solution. All right, D. Here we go. Now we have an x squared and an x term. So we're going to want to set it equal to 0 and try and factor. Since I want my 2x squared positive, I will subtract 10 from both sides. So we get 2x squared minus x minus 10 equals 0. Now, we have a case where a is not 1. So we do have a coefficient in front of x squared that's not just 1. So when that's the case, ax squared plus bx plus c equals 0. We can use what I like to call the star method. This is just one of many strategies. But one method is where you multiply a and c. So it multiplies to ac and adds to b. And then we find those two numbers and we'll place them in the lower spots. But then we take our ax squared term and just make it ax. And then we'll need to reduce, but I like to show this in context. So in this case, I'm going to multiply a and c. So I multiply 2 times negative 10 to get negative 20. And that's what goes on top, what multiplies to negative 20 and adds to negative 1. So we play around with it and we come up with 4 and negative 5. Now this is the tricky part. We're going to take that 2x squared and we just make it regular 2x. And we put it in both locations, both of those remaining locations, in the top left and the top right. And if if we cannot reduce these, so our two factors are kind of right here and here. But if it can be reduced, we need to do so. So notice like the 2x minus 5, the 2 and the 5 cannot be reduced. So 2x minus 5 is in fact one of the factors. However, we have 2 and 4 can be reduced. So we do, and we reduce that to x plus 2 because we can reduce those both by 2. And so our other factor will be x plus 2. And of course, you could always multiply this out and check that it's correct. But here we have this equation is now factored set equal to 0. So we can set each factor to 0. So 2x minus 5 equals 0 or x plus 2 equals 0. To solve, I can add 5 to both sides and then divide by 2. And over here, I get x equals 5 halves. On the left, we'll subtract 2 from both sides and get -2. And so our two solutions are -2 and 5 halves. All right. So for our last quadratic equation, we're going to go ahead and see what we can do with x squared equals 5x plus 2. So again, since we have an x squared term and just an x term, we're going to set it equal to 0 and try and factor. I'll subtract 5x and 2 from both sides. To get x squared minus 5x minus 2 equals 0. So the first thing we want to do is see if we can factor this. So it multiplies to -2 and adds to -5. So we can try 1 and 2 with one of them being negative, but those are not going to add or subtract to -5. So this is not factorable over the rationals. So what we can do is we can now go ahead and use the quadratic formula. And it's to find x, we can plug in -b plus or minus big old square root b squared minus 4ac all over 2a. And that will give us our solutions to this quadratic equation. So notice we have a is 1, that's the coefficient in front of x squared, b is -5, the coefficient in front of x, and c is the constant, -2. So let's plug these in. Negative of -5 plus or minus big old square root, -5 squared minus 4 times 1 times c, -2. All of this over 2a, or 2 times 1. So for these, I like to take the square root and just simplify that first. So -5 squared is 25, and then I can do the minus 4 times 1 is just 4, and then I'll multiply that by a -2. And so that ends up giving me 25 plus 8, since I have this minus 4 times a -2, which is the square root of 33. And now I'll put it back in and say, okay, negative of -5 is just a +5 plus or minus square root of 33 all over 2. And so since we cannot simplify that any further, we are now done. I decided to add one more example to practice the quadratic formula, especially when it comes to simplifying it. And here we're going to do 4x minus 1 equals -2x squared. So again, I have an x squared and an x, so I want to set it equal to 0. And here, because my x squared, the coefficient is negative, I'm actually going to add 2x squared to both sides so that my coefficient in front of x squared ends up being positive. So I get 2x squared plus 4x minus 1 equals 0. We can try and factor that. We say, okay, we have to multiply a and c. So what multiplies to -2 and adds to 4? Again, we'll see that doesn't work. There are no integers that multiply to -2 and add to 4. So we'll go ahead and use the quadratic formula where a is 2, b is 4, and c is -1. So we get -4 plus or minus big old square root 4 squared minus 4 times a, which is 2, times c, which is -1, all over 2a, or 2 times 2. Again, let's simplify under the square root. 4 squared is 16, and then minus 8 times -1. This just turns into square root of 16 plus 8, or square root 24. But rad 24 can be simplified since 4 goes in evenly to 24, and 4 is a perfect square. So we could rewrite that as rad 4, rad 6, or 2 rad 6. So now let's go back to our big formula. We get -4 plus or minus 2 rad 6 all over 4. I multiplied 2 times 2. And since we can simplify all of the numbers outside of the square root, with -4, the 2, and the 4, we can reduce those all by 2. So one strategy is let's factor a 2 out from the numerator, and we're left with -2 plus or minus rad 6 all over 4. And now that we have this multiplication over division, we can simplify the 2 and 4. So our final answer here will be -2 plus or minus rad 6 all over 2. And that is a quick overview of solving various quadratic equations. Next, we're going to look at one-to-one functions and their inverses. So let's first review what is a function. It's where each input corresponds to only one output, or similarly, each x value corresponds to only one y value. Now, when we were looking at functions graphically, we could test to see if a graph was a function or represented a function using the vertical line test. And that was every vertical line could cross our graph at most once. Well, now we're going to look at a certain type of function. So now we're going to have kind of the opposite also be true, where now each output corresponds to only one input, or each y value corresponds to exactly one x value. So now we will use the horizontal line test. Which, in order to be a function, all horizontal lines must cross our graph at most once. So in order to determine if a function is one-to-one, first we need to decide if it is in fact a function, and if it is, then we will use the horizontal line test to see if it is one-to-one. So if we have y equals x squared, we got to decide, hey, is it a function? Well, we have to kind of imagine as many, all vertical lines, and making sure that they pass through our graphs at most once. So here we can see that every vertical line, if you kept drawing vertical lines, they would all pass the vertical line test because every vertical line will only cross that parabola once. So yes, it is a function. Similarly, we could see if we plugged in an x value here, we could plug in 5. 5 squared is 25. or we could plug in any value for x, and it will get just one value for y. Now, is it 1-to-1? Well, now we're going to utilize the horizontal line test. So we might take any horizontal line, maybe down here, it's safe. It doesn't cross our graph at all. We could take that x-axis. It's also safe. It just crosses our graph once. But if we take another line, like let's say y=4, we can see it crosses our graph at two different places. So this fails the horizontal line test and shows that this is not a 1-to-1 function. Similarly, we could see if we looked at y=x² and we plugged in 4 for y, if we went to solve 4=x², we could do that. We could solve by square rooting both sides, but we need a plus or minus. And that will give us that x is plus or minus 2. So given one y value of y=4, gave us two different x values. X could be 2 or x could be -2. So this is not 1-to-1. All right. Next, let's look at 1=x² plus y². So here we have an equation of a circle of radius 1. And the first thing we need to do is decide if it's a function. And so that would mean it has to pass the vertical line test. So you could see there's many vertical lines that pass through our graph more than once. So right away, it fails the vertical line test. So it's not a function and therefore cannot be a 1-to-1 function, because 1-to-1 functions are just a subset of our functions. Last but not least, let's take a look at y=x³. So here, first, let's decide if it's a function using the vertical line test. So each of our vertical lines are, in fact, passing through our graph exactly once. And then now we'll see if it's 1-to-1 using the horizontal line test. And again, all of our horizontal lines are passing through our graph once. Even that x-axis, when we're at that x-axis, it only passes through at the origin. So yes, this is a 1-to-1 function. All right, so one of the main, or one of the very important applications for 1-to-1 functions is if a function is 1-to-1, then it has an inverse. So you might be thinking, you can start thinking of like inverse operations. Multiplication, the inverse operation is division. If we have subtraction, the inverse operation is addition. So that all of that comes into our inverse functions. What we want to think of is if f, let's say f will take a to b, then the inverse will reverse that process and take b back to a. And so just a few things about notation. So if f of x is our function, then we use this inverse. It looks like f to the -1 power, but it's just the notation that we use to indicate the inverse. So f inverse of x. All right. One thing we will notice, again, if the function takes a to b, then the inverse of that function will take b to a. So therefore, our domain of f will be the same as the range of f inverse. Similarly, the range of f will be the domain of f inverse, because they are kind of doing the opposite functions. Also, if we have AB on the graph of f of x, so in this case, if we're taking a to b through f, so we got f of a equals b, or the point AB is on f, then the reverse will be true, that the inverse of b will equal a, or BA will be on the graph. So what you want to think of, if you go between your regular function and its inverse, the inputs and outputs switch. Okay. And then one aspect of inverses or one piece of inverses is, well, what if the function's not one-to-one? Does that mean you just can't find an inverse? Unrestricted, yes. However, oftentimes we really do need an inverse, but what we have to do is we have to restrict the domain to make the function one-to-one, and then we can find the inverse of that section. So that's going to be really important because all of our trig functions are not one-to-one. So actually, let's take a look at that. Let's look at y equals sine of x. Notice it passes the vertical line test, but so it is a function. However, it does not pass the horizontal line test. If I graph y equals 1/2, oops, 1/2, for example, you can see it crosses many, many times. Similarly, we could look at y equals secant of x and look at y equals, so first we can look at the vertical line test. It is a function because every vertical line passes through the graph at most once. But if we look at, say, y equals 2, we will see it fails the horizontal line test. And last but not least, we can also look at y equals tangent of x. And we see, because it being a periodic function, even though it passes the vertical line test, it fails the horizontal line test. So let's end the subskills section today with looking at how we actually find an inverse. So this is more of a strategy here and how we can do that. So if we take, and I'm going to, actually, I want to come back real quick to this restricting the domain. So I want to look at one that's pretty familiar, a function that's pretty familiar, which is y equals x squared. So if we look at y equals x squared, that's a graph of a parabola. All right. And we can see, as we did in a previous example, we saw that it is a function, but it's not one-to-one. So that's a problem. So what we could do is we could restrict the domain and just look at part of that parabola. And in this case, I'll just say, oh, let's just say x has to be greater than or equal to 0. And now you see we have a one-to-one function. So if we only take that right half of that parabola, or from x being 0 to going to the right, we have a function and it's one-to-one. So now we could go ahead and find the inverse of this. So let's go ahead and do that. And if I wrote this instead as f of x equals x squared, then I'd first replace the f of x with y. Okay, but I already have it in terms of x and y. So as soon as I want to show, okay, well, what happens to the inverse? Now I'm going to switch x and y. So I get x equals y squared. So this is a different function altogether. As soon as you switch your variables, it's a totally different function, but it could describe the inverse. So let's solve for y. So I will take the square root of both sides, remembering to do the plus or minus. And now I get y equals plus or minus rad x. But we actually don't want both pieces. If we have x is greater than or equal to 0 of our original function, then what that tells me is that for my inverse, remember x and y are switched, then we know that y has to be greater than or equal to 0. Well, if that's the case, then I only want to take the positive square root of x. So I have square root of x equals y, or if we were to use the function notation, as in we, instead of y equals x squared, we had f of x equals x squared. Then we can use the inverse notation of f inverse of x equals the square root of x. So if we restrict the domain to make sure it's 1-to-1, then we can find the inverse. And one of the strategies is switching x and y, solving for y. So let's go ahead and do this with some practice. So first we're going to decide if it is 1-to-1, and if so, we'll go ahead and find the inverse. So y, or f of x equals x cubed plus 4. There are a few different strategies to determine if it is 1-to-1. One is if we're familiar with the graphs. So we just looked at it up above. A cubic function is looks sort of like that. It goes through the origin and it increases over all of the real numbers. But we have this plus 4 here, which will shift our function up 4 units. So notice it doesn't really change the shape much, it just shifts up 4. So it will pass both the vertical line test, showing it is a function, and it'll pass the horizontal line test to show it is 1-to-1. So now we can find the inverse. So we could rewrite f of x using y. So y equals x cubed plus 4. And then when we switch to find the inverse, we can switch x and y. X equals y cubed plus 4, and then we will solve for y. So subtract 4. X minus 4 equals y cubed. And now we'll do the cube root of both sides. However, because it's an odd root, we do not need the plus or minus. So we get the cube root of x minus 4 is y, or utilizing inverse notation, f inverse of x equals the cube root of x minus 4. All right. So now we have, for part B, we have a list of ordered pairs. We have 3 ordered pairs here: 2, -3, -4, +3, -1, 5. So to verify that it is a function, or to verify that it is 1-to-1, first we need to verify it's a function. And notice none of our x values repeat. So each x value is corresponds to exactly one y value. Similarly, none of our y values repeat. So each y value corresponds to exactly one x value. So yes, it is 1-to-1. And to find the inverse, all we need to do is switch our x and y. So instead of 2, -3, we'll have -3, 2. Instead of -4, 3, we'll have 3, -4. And last but not least, instead of -1, 5, we just switch it to get 5, -1. And there we have our inverse of that function. Okay, so for C, if we happen to know the shape of this graph, which is if we knew that y equals square root of x is actually a parabola, half of a parabola on its side opening up, then we could determine, oh, the square root of x minus 1 will just shift 1 unit to the right. So it is a function and it is 1-to-1. Algebraically, we could also determine if I give any x value, I will get exactly one y value out. And that's a little bit more through exploration. So let's go ahead now. I'm going to rewrite my original function just using y instead of function notation. And now I will switch to the inverse, which means I'm going to switch x and y. So x equals the square root of y minus 1. And now I will solve for y. So we square both sides. X squared equals y minus 1. And we'll add 1 to both sides. So we get y equals x squared plus 1, or using function notation, h inverse of x equals x squared plus 1. However, we need to make sure that we are limiting the domain properly here, because this function here is 1-to-1, but x squared plus 1 is not 1-to-1. So what we might notice here is x on our original function of h of x is greater than or equal to 1, but y is greater than or equal to 0. But in order to use any of this information about the original function for the inverse, I'm really wanting to focus on x of my inverse. But x in my inverse corresponds to y from the original function. So I will switch my y to x and get that x must be greater than or equal to 0. And then last but not least, let's take a look at if we have k of x equals 3x squared minus 1. So here, we need to decide, is this a function and is it 1-to-1? So remember that y equals x squared is just a parabola opening upward. So the 3 will be a vertical stretch. The 1 will shift down 1 unit. And so it is 1-to-1, or this is a function, but because it fails the horizontal line test, this is not 1-to-1. So because the directions say only if it is 1-to-1, it then find the inverse. But just so you know, we could restrict the domain and find the inverse of the function with the restricted domain. But for this purpose, we'll just go ahead and stop right there. So now we'll get ready to look at inverses of trig functions. So, thank you.